Welcome back to Physics 141 Online. What I'd like to do today is give you another example problem involving the use of projectile motion equations. And this problem and the sketch is actually from a book that I was given, a very unusual book called Physics for Dogs. So, here's the problem statement. Fido sees his toy ball in a pool and wants to get it. Being a smart dog, he knows his maximum running speed is 5 meters per second, and he estimates the distances shown in the sketch, d1 of 1.75 meters, and h, which is the height that the edge of the pool is above the water, as 0.2 meters. If Fido runs horizontally off the edge of the pool, will he land in the water short of the ball or past the ball? I suppose it's possible he could land on the ball, but we'll see that that's not the case. And then, based on our answer to part A, let's find the launch angle Fido would need in order to land on the ball. So, there's two parts to this problem. There's A and B, and we will break those up in two pieces here. But first, let me establish the coordinate system, because Fido here is jumping to the left, and it would make sense for us to choose the coordinate system where, of course, y is vertically upward, but x, let's make x increasing to the left. So that is just, we could rewrite the sketch, but because this is the way the sketch was set up, I thought I would stick with it. So x will be increasing to the left. So for part A, of course, if we want to identify the problem type, we know that that's the first step. And here we've got 2D motion, and it's projectile motion. And so all of the projectile motion equations are going to be useful, or at least possible for us to use in this problem. So for part A, what are we trying to find? We're trying to find whether he will land short of the ball or past the ball. So before I even make a list of the given, I'm going to write down what it is we're trying to find in part A. And clearly, to figure out whether he will land short of the ball or past the ball, we need to find delta x. What's his horizontal displacement as he makes the jump running off the end of the pool horizontally into the water? And so what are we given in part A? We can see that in part A we're given delta y, because delta y, that's equal to minus h, and there's a numerical value for it here. I will just leave it as delta y, and then we'll plug in 0.2 meters when we're ready to calculate delta x. What else are we given? We are given v0. We're given that Fido's maximum running speed, which we will assume he uses, is 5 meters per second. And then, of course, since this is a projectile motion problem, we know what the acceleration is, negative g. So the strategy that we're going to use, which is very, very common in projectile motion problems, is we're going to use the equations for delta x. Delta x is equal to v0x times t, and then we're going to use delta y, because that is v0y t minus a half gt squared. Okay, now in this problem, since Fido in part A is going to jump horizontally, that's very special. A horizontal jump would mean that the v vector initially, of course it would be up where Fido, actually let me fix that, up where Fido is standing. So the initial v vector would be like that, v0, and it would not have a y component. And so we can see another piece of given information is, for this part, v0y is equal to 0. So that's going to drop out of the delta y equation. v0x then, since all of the v0 vector is in the x direction, we also know that the x component, v0x, is the same as the initial speed, v0. And it's positive because x is positive to the left. So now let's use those two pieces of information to rewrite our equation. Delta x is v0 times t, right? Because v0x is v0. Delta y is now just negative 1/2 gt squared. All right, so here's the strategy. We've got our equations, and now we're in the execute part. We did the identify, we did the setup, which was the S, and that had to do with making a list of the given information and then determining which equations we would use. And now we are in the execute step, which is going to be doing the algebra that's necessary to solve for delta x. So delta x, we know v0, we'd like to find t, but we can't find a numerical value for t directly unless we use the second equation. But of course, rather than calculating a numerical value for t, let's solve for t. All right. So if we solve for t, we multiply both sides by 2 and divide by g. So we get 2 delta y over g is equal to negative t squared. And if we just turn that around and solve for t, t then would be square root of negative 2 delta y over g. And I could plug that in and get a number, but there's no reason to, because I don't need to find that number. So what I'm going to do instead is take this expression for t and plug it in up here for delta x, because delta x is what I'm trying to solve for. Remember, as I've stressed in class, don't plug any numbers in until you're ready to solve for the quantity that you're actually looking for, which is delta x. So delta x is v0 now times the square root of negative 2 delta y over g. Now we're ready to plug numbers in because we have an expression for the quantity that we're trying to find, delta x. We want to know how far, at the speed that's given, how far Fido will travel horizontally by the time he falls into the pool. So now we can use this expression and the numbers. And we're going to also carry units along. So v0 is 5.0 meters per second. And I'm going to enlarge the square root because I'll need room to put in all the numbers. Negative 2. The negative sign is important because delta y, look at what I did in my given information. I made the same mistake that I've talked about in class. I wrote that delta y is 0.2 meters. It's actually negative 0.2 meters because the dog ends up below the starting point. So that should be negative 0.2 meters. And then we divide by g, which is 9.8 meters per second squared. Let's look at the units under the square root. We're going to end up with, the meters will cancel, and we're going to end up with 1 over second squared in the denominator, which means second squared in the numerator. Square root of second squared is just seconds, and seconds times divided by seconds will cancel, and we will get an answer for delta x in meters, which is what we should get. All right, so let's now finish it off. Equals, if we plug all these numbers into the calculator, we find that delta x is 1.01, and again, it's meters per second out here times the square root of seconds squared, right? And so we end up with 1.01 meters. So what does that mean? That's our numerical answer. It means that by the time Fido lands in the water, he's only traveled 1.01 meters. And so he lands in the water. His actual trajectory with a horizontal takeoff is something like this. He lands down here and he falls short of the ball. And so the answer to the question is short of the ball. What does that mean? Well, that means that when we do part B, Fido is going to need to have a positive launch angle, right? He's going to have, if he wants to get a little further, he's going to have to take off at an angle theta above the horizontal. Now, what if our answer had been 2 meters? If our answer had been 2 meters, right, it would mean that Fido overshot the ball, and he would probably then want to take off at a downward launch angle in order to hit the ball. But in this case, so he needs to have an initial takeoff angle greater than 0 degrees, because it was 0 degrees in this problem. All right, so hopefully that makes sense. You might want to stop the video and review this and make sure that you understand. Of course, I skipped the very last step, E, which was the evaluate step. So let me just go ahead and mention that. We executed the solution using the equations. Units, They're correct. The distance makes sense, right? It's something close to the 1.75 meters given in the problem. So we don't know for sure if that means it's correct, but certainly if the answer had been 1 centimeter, we would have expected that there's something wrong with that, because at 5 meters per second, you shouldn't land 1 centimeter away. So the distance is reasonable, and of course it's positive as we expect. The sign, right, greater than 0 is what we expect for this. So all of those things lend themselves to supporting our answer as being a reasonable answer. All right, now part B is find the launch angle that Fido will need in order to land on the ball, because clearly we found out he doesn't land on the ball with a 0-degree takeoff angle. So let me erase some of this, and then we will do some work to solve for the angle. And the angle solution, it's not really hard to set up, but the algebra that's necessary in order to get the answer is a little bit tricky. So I'm going to outline the steps for it and then just give you what the answer is, and you can verify or confirm that my answer is correct if you want to. So in this kind of case, we are not going to have the same simplifying factor. The takeoff will not be horizontal, right? And so as a result, even though we will use the same equations for delta x and delta y, we will not be able to get rid of the launch angle. In fact, the launch angle we want to be in the equations, because that's ultimately what we're trying to solve for. So let me just keep on going here with a little bit more eraser action. So you might write down, as you're waiting for me, you might want to write down the delta y equation, because we're going to start with that again. So that is, we have the delta x equation up here. The delta y equation is, right, I got to go back to the pen now. So delta y is v0y t minus half g t squared. And so let me just fix this up a little bit. Now we're working on part B, and in part B we don't want to find delta x, we want to find theta. So theta is going to have to be in our expressions. We're given the same value for delta y. We're also now given delta x, because if Fido is going to land on the ball, delta x is 1.75 meters. So now we have to get the angle into these expressions, and remember, the takeoff is now no longer a horizontal takeoff, so I'll erase that part of it, and now we will use the part of the sketch that was already there. And unfortunately, I've managed to erase the angle, so I'll put that back into the sketch here. So the takeoff angle is theta, and the takeoff velocity vector should be a straight line, but it looks like that. So using our trigonometry, you'll get really good at this if you haven't been working on it too much yet. Delta x, the v0x, is actually the magnitude v0 times the cosine of theta multiplied by t, and now delta y is v0 times the sine of theta times t minus the usual 1/2 gt squared. And so what's the strategy here? We're trying to solve for theta, so what we will do, and now we're in the execute phase again, we've set the problem up. We've identified, of course, what problem type it is. We're going to solve for t from the delta x equation and then plug it into the delta y equation. So here we go. T from the delta x equation is delta x over v0 cos theta. Right, and then we're going to substitute that into the delta y equation, but I'm not going to try to squeeze it in under the delta y equation because it's not going to fit there very well. So let me clear some space out down here underneath the sketch of the dog. So what we find is we're rewriting the delta y equation, but then we're subbing in the value for t into the delta y equation. So how does that work? Delta y now becomes v0 sine theta times delta t is delta x over v0 cos theta. And I see right away the v0's cancel out, so I'll just go ahead and do that. Now minus 1/2 g, and now we take this t quantity and we're going to square it. Delta x over v0 cos theta squared. Everything inside the parentheses gets squared. All right, so we will persevere here and see what we can do. The first thing that we see is that we can write delta y then as delta x, and I could write tan theta, but I have reasons for not wanting to do that right now. Sine theta over cos theta, right? And then minus 1/2 g. Now delta x gets squared in the numerator, and then in the denominator we have v0 squared cos squared theta. And it's not obvious here exactly how we're going to solve for theta, but notice that this equation, in principle, will allow us to solve for theta, because if we look at the equation, we know delta y. That's given to us. We know delta x. We know g, and we know v0. So everything in this equation we know except for theta. So now this will give the solution for theta. It's not so obvious how we're going to get that. We can't do it in one step, but in principle we have finished the solution to the problem except for actually doing the necessary algebra. So the way I'm going to do this is to multiply through by cosine squared theta. All right, so multiply both sides. Cos squared theta. Why do I want to do this? I need to get the cosine term out of the denominator. So when I do this, the left-hand side becomes delta y cosine squared theta. The right-hand side, if I multiply this first term by cosine squared theta, I get delta x sine theta cosine theta. And then the last term is minus 1/2 g delta x squared over v0 squared. All right, now that doesn't seem like I've necessarily made things any easier, but there is now a way to finish the problem off, and that's going to be to do the following. I need to get rid of the sine somehow. I need to get an equation that only has cosines in it. So here's what I'm going to do. I am going to take the expression for the delta x sine theta cos theta and solve for it. So delta x sine theta cosine theta equals, I'm just adding the quantity 1/2 g delta x squared over v0 squared to both sides. So I get delta y cosine squared theta plus 1/2 g delta x squared over v0 squared. All right, so I've just rearranged this. Now I'm going to square both sides. And the reason, you'll see why I want to do this in a minute. So squaring both sides, now I have to do some erasing here so that I can clear some more room up on top of here. And now I'm going to completely get rid of the sketch and everything else that's in here so that I can have a little more room to do the final necessary work. And by the way, this is a problem that is far too complicated for me to give as a quiz problem, so don't worry about that. But I do want to show you that it can be done and just outline the procedure for doing it without necessarily showing all the numerical steps. But it's kind of satisfying once you've gotten a problem given to you to be able to solve it. And honestly, it took me a while to be able to look and see what the method was for finding that angle theta in this problem. But it's kind of gratifying that it is possible to do it. So, squaring both sides, on the left-hand side that's easy because there's only a single term. On the right-hand side, I'm going to have to do the FOIL method for squaring an algebraic expression. So, squaring both sides. On the left, then, I get delta x squared sine squared theta cosine squared theta, right? Equals on the right. Now remember, it's the first. You square the first term, then you square you multiply the two together, and then you do the multiply the two together again, and then you square the last term. And so this will be, the first term will be delta y squared cosine to the fourth theta, right? And then I'm going to have 2 times the product of those two terms. So 2 delta y times cos squared theta times g delta x squared, right, over 2 v0 squared, like that. So I multiplied these two terms together and then multiplied by 2, and then the final term, right, plus, now it's the last term squared. So it's g squared delta x squared over 4 v0 to the fourth. You can check and make sure I did that right, but I squared both sides of this expression. And now here is where you'll see the payoff, because now I've got terms involving cosine to the fourth, cosine squared, and then sine squared. And now there's a great trig identity that I can use where I can replace sine squared by 1 minus cosine squared theta. So 1 minus cosine squared is sine squared, and then that's still got a cosine squared in here. And now we've got everything on the right-hand side. And I'm not going to rewrite it. I'll just leave it, you have it right there. So the left-hand side, when I multiply it through, I'll get delta x cosine squared theta minus delta x cosine to the fourth theta. All right? And that's equal, again, to everything on the right-hand side. So what's going to happen here is that I am going to be able to collect all the terms and get them all on one side of the equation. And I'm just going to outline, I'm not going to actually go through the rest of the rearrangement, but I'm just going to outline what it will look like when you carry this all the way through. And you will actually get something where we can use the quadratic formula to find the solution for theta. And here's the big picture of how it works. So what's going to happen is, in the next step, I'll move all the terms over to the left-hand side of the equation, get everything on the left, and then on the right it will just be equal to 0. So what's going to happen is, I'm going to have some collection of terms times cosine to the fourth theta. And then I'm going to have, again, some collection of terms times cosine squared theta, and then I will have a final collection of terms which will just be the constant term. All right? And now, notice what's going to happen then is this I can call A, this I can call B, and this I can call C, and I can get numerical values for those quantities. And then, when I do that, I will be able to apply the quadratic formula and solve for cosine squared theta. Because just compare this to the form of a quadratic equation. remember the general form for the quadratic formula is a x squared plus bx plus c equals 0. And so I have exactly the same thing here, except instead of x squared, I've got cosine of the fourth. Instead of x, I get cosine squared. Remember that the solution, when you solve the quadratic formula, x is what you're solving for. Negative b plus or minus the square root of the familiar b squared minus 4ac, all divided by 2a, right? So I will, once I get the numbers a, b, and c, and I can calculate all those after doing the necessary algebra, then I'll be able to plug into the quadratic formula, except what I'll be solving for is not x, but cosine squared, right? So that's what I'll get. In this case, it'll be cosine squared theta. And when you plug in the values for a, b, and c that come from the work shown above, you actually get two solutions because of the plus or minus sign. There's actually two possible angles that Fido could use as a takeoff angle. So theta 1 would be the smaller of the two angles, 11.5 degrees, and then theta 2 would be the higher of the two angles, which is 80.7 degrees. Probably not too surprising if you have a problem like this over level ground. If delta y is equal to 0, there's always two possible angles that will give you the same horizontal distance, and that's also the case in this problem. So Fido could decide he could either take the shallow launch angle of 11.5 or the much steeper launch angle of 80.7, and they would both land him in the water on top of the ball at the same place. So I hope you'll not worry too much about the really messy algebraic work that led to the ultimate solution for theta, but focus more on part A and also on the setup of part B, because those are techniques that you'll use on many homework problems in this part of the course. I hope this helps, and I'll see you in class.